Okay, so today we're going to talk about dynamic allocation. Um, so this is so the cool thing about dynamic allocation, of course, is if you've got long-running jobs like databases or servers, you can allocate and deallocate on the fly, as opposed to JCL, where it gets allocated before your program starts and it stays allocated. So that can be a problem if you're trying to run backups and that sort of thing. If your server has data sets that are allocated that are open, it can be a problem. So dynamic allocation is cool because it makes it very fluid. So when you allocate in JCL, you use DD statements, and DD statements contain parameters like disposition, new, catalog, delete, just like this. Dynamic allocation it's different. It's analogous, but these these concepts like disposition, new, catalog, delete are tokenized, and it's very granular. So in this example, there are three separate tokens: one to do the first positional disposition, another to do the second, another to do the third. And when you invoke dynamic allocation, you use the dynalloc macro. Some people code SVC99 because dynalloc really doesn't do anything except issue an SVC99, but really it's a best practice to code the system macro, even though it only generates this one statement. So do that, please. So there's a couple of things that dynamic allocation does not support, and it kind of makes sense. Like the idea you cannot dynamically allocate jobcat, stepcat, joblib, or steplib. And really that makes perfect sense because they're supposed to be in place when your job starts. It affects the beginning of your program, how it starts. And so it wouldn't make sense to have a program running and then dynamically alter these environments. So they just don't allow that. A few other things they don't support is checkpoint. You can't have DD name references, and you can't have DLM, which goes with DD asterisk or DD data. And it doesn't support this DSID, which is really old. It's basically obsolete. It's used for identifying floppy drives, floppy disk drives. And then certain subparameters like DCBs, cylinder overflow, NTM, and record key position, relative key position. Those are ISAM parameters which have been dropped support for many years. It doesn't support disk pass. I'm not sure why. And then space, absolute track addressing. It doesn't support that. And it doesn't support units, AF, or volumes retained parameters. But other than that, everything that you can do in JCL, you can do with dynamic allocation. So there are various services you can invoke, and today we're going to talk about allocation and deallocation or unallocation. Next time we're going to look at concatenation and deconcatenation, but there's just several different services that SVC99 can give you, and we'll talk about a couple of them here today. These are the primary ones: allocation and unallocation. And the verb codes that are used in the control blocks are in this IEF ZB4dog0 macro. There are a bunch of equates in there. Also, in that same macro are various desects. Now, I know this is really busy right here, but this is everything in context. So on the top here, you'll see these names. These are desects that are in this generated by this macro down here. So there's an S99RB pointer, which is nothing more than a full word address pointing to the S99RB, and the high order bit it's got to be on to indicate end of list. So it's just one parameter, one word. The S99RB is the primary control block. It contains, among other things, the verb code. Which service are you really wanting? It's got a place for error and info codes. And then there is an address of it's called the text unit pointer. And the text unit pointers, this is S99TUPL, it's nothing more than just a list of addresses. And the very last address in the list has the high order bit on to indicate end of list. And these are text unit pointers. And so they also point to text units. Now, in the text units, the first two fields here. These are 2-byte fields. The first two fields are fixed format. The first 2 bytes contains an allocation key. It says what we're representing here, and then the number of occurrences of a length parameter pair. So most parameters, there's just one of them, so that you would see the key value 1, a length of that value, and then the value. Some are reserved and have no parameter area, so it's just the key and a 0 here. But other parameters like volume, for instance, you might have multiple volumes, so it would say like 3 here, and then you have a length and a parm, and a length and a parm, and a length and a parm to have those Valseers, and the length in that case would be 6. There's an optional S99RBX, an extension block, and there's a pointer in here that points to it, and this can be zeros. This is optional, and this is useful though, and we're going to talk about it today because you can get additional error information, detailed error messages that can be very useful in debugging a problem. So hopefully this makes sense. You know, the pointer to the control block, a pointer to the text units, the list of text units, and then these variable length text units over here that has a fixed length header, but the rest of it is wide open. We'll look at each of these blocks separately, independently. The first, the S99RB pointer, it's very simple. It's a one-word field that contains the address of the S99RB, and the higher order bit is on. The S99RB itself, it's got several fields. The first one is the length. It's a 1-byte length of the control block, and you can assemble it in using this expression, the end of the control block minus the beginning, and that calculates the length, and that's what you would assemble into it. Then the verb code, and today we're talking about allocation and unallocation, so these are the two equates that we'll be dealing with today, and then several others that are possible. You've got a S99 flag 1 field, which is 2 bytes, and they're named S99 flag 11 and flag 12. So flag 11 has these, and a lot of times you don't need any of these. We're going to look at this one today, the S99 no convert. It means don't try to find an existing allocation. This is a brand new allocation request, so this will be on. And other options are, you can say I want to use an existing allocation if it's got the convertible attribute. We don't need to deal with that. You can designate that you don't want to mount volumes or consider offline devices, which would be interesting for tape devices. We're going to be dealing with disk devices, so we're not going to worry about that today. And other conditions here, like this conditional tie-out. So if you had a database and you can't tolerate being paused for any reason, then you might turn this on, saying if you can't get the tie-out in queue, then just fail the allocation. I don't want to wait for it. And other specialized things like for GDG use locate to determine the relative generation number, which means you're giving them instead of an absolute generation number, you're giving a like 0 or -1 or +1, and you'll have to use locate to resolve what is the absolute generation number for that. This one is useful sometimes. It's a silent allocation. There's no messages that get issued, so if you turn this flag on, you won't see any evidence that an allocation occurred. And then this last one, which I think we did turn on in the test program, it says if this data set has been archived, I don't want to wait for it to get recalled. So if it's been archived, don't bring it back from archive. Just fail the request. And the second byte of the flags, you've got a couple of other specialty things. Normally, you can embed symbolics in the dataset name, the member name, and the volume serial number. So if you want to, if you embed those symbolics, normally they're resolved for you automatically, those system variables. But if you, for some reason, you want to disable that, you can turn this flag on. I don't know why you would want to disable it. When this flag is on, it means you are giving an actual UCB address rather than a symbolic reference to a unit. And then here's two ways. This is the old way of getting a DSAB built above the line. You turn this bit on, but nowadays you would turn this bit on. and it says, I'm giving you a real 4-byte UCB, and I want an extended tie-out. These other bits are not defined yet, not referenced. There's a 2-byte reason code, so if there's a failure, you get a reason code and an info code that will more exactly explain the problem. And you have to have the text pointers, the text unit pointers, so this is the address of that list of pointers. And then if you have an extension block, an S99RBX, you would put its address in this field. Otherwise, you would put zeros there to indicate there's no extension. And then lastly, in the control block, there is it's called flags 2. There's 4 bytes that are named flags 21, 22, 23, and 24. And 23 and 24 aren't really defined yet. They're just zeros. Anything that's tagged with this little stop sign here means that it will potentially hang up your job. Like this one says, I'm willing to wait for volume to become available, and that's usually a tape consideration because you cannot share tapes like you can share DASD. So if another job has a tape volume, you would have to wait until they're through with it before you could get it. This one says willing to wait for a data set. It's the same kind of a problem. If you're trying to get a data set disk equals share and somebody else has it disk equals old, you can't get it immediately. So it says I'm willing to wait for that data set. This one, I would not recommend ever using this one. It's very dangerous. It says don't issue an NQ, assist-DSN NQ for this data set. I don't know why you'd want to do that. It must be a very special case. So don't do that one. This flag says I'm willing to wait for devices, and this is typically for tape. So normally what happens is you'll have 2 or 3 systems that are sharing a set of tape drives, and the tape drives are varied offline to most of the systems, but they're varied online to certain systems that are using them. And then if you need a tape drive and you've got this flag turned on and you tried to allocate a tape and there's no tape volumes, there's no tape drives available, then it will issue WTO to the operator saying, hey, this job needs a tape drive. And the operator can look around and say, oh, here's one that's not being used on this system. I'll vary it offline over here, and I'll vary it online on the current system. And then it'll reply to that allocation message saying, here, use this device. So it's just a way of not failing jobs just because certain devices are not available. Another flag saying, consider offline devices. These would probably both be on at the same time. And again, it's typically you're looking at tapes, not disk. If you're a system resource or system service, you might already have the tie-out NQ for this for the job step, and if you did, you would turn this on. Otherwise, you would not normally use this. And the catalog, this is for system internals. It has to do with allocating a catalog data set or a catalog specifically, and you normally would never use this. This is for the operating system use. And this last one, mount, says volumes can be mounted if this is not set, if the no mount is not set. A couple more bits here. The DevT flag says that I've given you a DAL unit text unit, but instead of being an actual unit name or generic unit, it's going to be a device type in the form of a dev type, which is just bits that are turned on. This actually is the same thing as UCB type. Just describes the device in terms of bit patterns. And there are a couple of bits that need to be turned off that have to do with sharing that are not relevant in this context. So you would need to make sure that the sharing bits are not turned on. We have here, do not perform JES3 dataset integrity processing. I would not recommend doing that. JES3 is just about, it's not really obsolete. There are people that have JES3, but it's very uncommon. And then finally, we've got these other two here. This DD level accounting suppression, this is something special that we normally don't use. Both of these flags, building the extended tie out above the line, these both require APF authorization, so you would typically not be dealing with those. The text unit pointer list, it's pointed to by the S99 TXTPP field of the S99RB. It's just a stack of addresses, text units. It points to the different text units that are part of the allocation. And as all variable lists are, you would have to have the high order bit on to signal the end of the list. And finally, the most complicated one is the text units. So there are typically 4 fields involved. So you've got this 2-byte allocation key, and there's a whole bunch of these equates that are in this IEF-ZB4dog2 macro that have to do with allocation, unallocation, concatenation, deconcatenation, various the various functions that you could do with SVC99. So these keys designate the specific thing that you're dealing with, like the dataset name or the DD name or whatever. Then there's that 2-byte field that says how many of the length parameter entries do we have. And most of them are just a single parameter, so you'd expect there would be a 2-byte length followed by the actual text unit itself. And like, for instance, the dataset name, you'd be 44 here, and then this would be the dataset name. Or if this was a DD, it would be 8 here, and then you'd have the 8-byte DD here. This macro, IEF ZB4dog2, has these desected fields that it will generate. So you would use this one as the standard one for your typical text unit, where you've got a 2-byte key, a number, which is typically 1, the length of that string, and then the string. But for fields that may repeat, like a volume serial number, then you would use this desect to map the second and subsequent entries, where it's length and then followed by the parameter, variable length parameter. And here's just an excerpt out of that IEF ZB4dog2. So for instance, if you're talking about dataset name, it's equated to this 1. Or if you're talking about, I'm sorry, that's a DD name, it would be just 1. Dataset name is 2. And so these equates will assemble in that 2-byte field, and it would just be a number. But you need to use these names to make it intelligible. When you're looking at your code, you want to be able to know for sure logically what are those text units. So use these equates for allocation. So they all begin with DAL, dynamic allocation, and all the ones for unallocation start with DUN, dynamic unallocation. And whereas like DD name happens to be a 1 here, it also happens to be a 1 here, there's not a 1-for-1 correlation between these. So when you're using allocation, use the DAL tokens, and when you're using unallocation, use the DUN tokens. And here's an example of coded. This is the DD name. We have, actually this is not, this is DS name. This is wrong. This comment is wrong. So DAL DS name is the 2-byte token. It ends up being a 2. We say how many occurrences do we have? 1. And here's the length parameter. So we've got the length of this field, which would be 44, and followed by the dataset name. Certain of these tokens ask for information back. So you'll see this is DAL RT. Any of them that start with DAL RT means you want to return information to the program, giving information to the program that the program doesn't have. In this case, we're saying, I want to know what the volume serial number is of this data set that I'm allocating. And dynamic allocation will, in response to this token, will return the vol ser of that where that data set is allocated into this 6-byte field right here. And the optional SVC99 request block extension, it's if you use it, and we will today because it gets you additional information on messaging, and that's why it's very useful. So it's got an eye catcher that's literally S99RBX in this ID field, a version, and there's an equate that you need to use called S99RBXVR. That's the value to set this version to. And the first set of options, it's just 1 byte. We could say the system, you want the system to issue the error messages before returning control. And if you turn this flag on, there's another flag you need to have turned on down here, saying that you want to use WTO if you're batch, and if you're TSO, you want to use the TSO put line. So we're not going to use these. What we want is that we're going to turn this flag on to say, I want the unformatted messages returned to me and then I will deal with putting the messages out in my log. There's more information here. These are unformatted messages, and there's another service that you use to format those messages where they're very presentable to the end user. You can turn this flag on to say, I want the message blocks below the line. If you're a mode 24, that would be what we're going to do, but we're not a mode 24 in our example program, so we're not going to turn that on. Yeah, you can also designate the storage key and the subpool that you want that storage to be obtained in if you want to. So if you're going to set the key or set the subpool, you would turn these flags on, and then there are other fields that you would set. Like in this case, if you turn this flag on, then you need to put the storage key to use in this S99E key. And if you turn this bit on, you would have to put the subpool number in S99EM sub. In our example program, we don't set either of those. We just get it in subpool 0 and just plain vanilla storage. We already talked about this. We're not going to be issuing messages via WTO or TSO put line. And here are those two fields we were just talking about, the subpool and the key. So you'd set those if you need to. Then for the messages being returned, you can designate what level that you want. So if you're only interested in error messages, serious error messages, you would set it to this Sev E, or you could set it to warn. But in our test program, we're going to set it to info, which means you could get messages even with return code 0, but you will get messages just about every time you issue it. And this will return them into an area that we're going to talk about here in just a second. This field will tell us how many, it's a 1-byte field that says how many messages were generated. And we'll use that to control how much storage we get later on. We'll talk about that. If you're running under TSO, then you would put the address of the command processor parameter list here, but we're not going to be doing that, so this will be 0 in our case. There is a 4-byte field with different messages in it. So here, a couple of them are not being used, but there are these couple of flags here. These are not actually set by SVC 99. These are set by the messaging facility that we'll talk about in just a minute. In fact, I'll just defer talking about them until we get there. There's a field here to get the return code from either the put line or WTO, which we're not going to have. And then finally a pointer. This is if messages are generated, then this will be the address of the message block. And in the previous page, we had the number of messages. So those two things were very important to us. And there is a general error code, an E error. It's a 2-byte code that is the return code for the information retrieval service, and a 2-byte code of the erroneous text unit. So those text units all have equates. If there's a particular text unit that was a problem, it will have the text unit ID here. So if it was the DD name, it would be a 1. If it's the DataSet name, it would be a 2. And it tells you which text unit had the problem. And then we also have this 4-byte SMS reason code. This gives a detailed reason why it failed. And the messaging routines will use that to create messages for us. And finally, we have this separate service called IEFDB476. And the way it works is you can generate these two Desects, and you use this IEFDB476 macro and generate a Desect1 and Desect2. Desect1 is the mapping of the parameter list for this program, so it shows you what fields need to be passed. And then Desect2 maps the messages that are formatted by this service. So kind of a high-level view of that is you acquire a gotten main area. You get the number of messages, which is that S99EN message, multiply it by 256, and that's the size of the area that you need to get. So you'll obtain that piece of storage. And then you'll use this EMDSect1 to map the parameter list. You'll build that parameter list. Then you'll link to this IEFDB476 service. And what it will do is take the unformatted messages and create formatted messages in your gotten main area. And it also will delete the messages that were created by SVC99, so it frees those up. And in that case, if there's a problem, we'll go back over here, he'll post the this S99ERCO is the reason code for the message service failure, and then a 1-byte reason code of why it could not free the message block. And this typically is not a problem. I've never seen this fail. So then, after you've called this service, you just navigate through the formatted messages using that Desect2, and once you have printed all your messages, then you free that gotten main area. That's kind of the overview of how you do it. So for this message service, this is the way it works: is you've got a word that points to the parameter list, the EM params. That's that Desect1 area mapping. And you got the higher order bit on saying that this is the end of that parameter list. So he points over here. You've got a function code, because this message service can format messages from other routines, like a dynamic allocation interface routine, the DARE routine. This function code, you say, I'm using SVC99. I've got SVC99 messages. You tell him how many messages there are, and then you have this pointer that points to the SVC99 request parameter list, and then it, of course, has that pointer to the extension, so it's got access to that whole parameter area. And then here's where you store the address of that buffer that you acquired, and it will format the messages in that area. So in our sample program for today, we have a utility called DynTest1, and it has a couple of verbs that it honors. It will list. Now in this case, we're going to say list syshut2, and of course syshut2 does not exist here, so that will fail. And he'll say, I want to allocate data set. Here's the data set name, and here's the DD name to use. So he's going to create syshut2 DD that's allocated to this data set. When we list it here, unlike the first time, it will list out the information. And this is the same list function that we had in our previous example, that SWA read. So it's the same stuff. It just lists out the dataset attributes. Then we will unallocate it, and when we list it again, it will not be there. So we'll get a failure here to prove that the unallocate worked. Then we'll say list syshut1. Now syshut1 we coded in the JCL. And then we will unallocate that, and then try to list it, and it will be gone. So this will say it's no longer exists. And we'll look at the details of the test program. So here is the allocation example. We have this S99RB pointer. It points to the SVC99RB control block, and it's got the higher order bit turned on. Here's our length of the control block. This allocates the space for the control block. This is the actual length stored into that control block. We're using the verb allocate, and then we used a couple of flags here. This is the new allocation, and if it's migrated, don't do the recall from archive. Fail it. And everything else is set to zeros except for the text unit pointers and the RB extension pointer. In the RB extension, you notice mostly we don't have anything set. We just have a few things turned on. We have the ID, which you have to have, the version, which I said you have to use this version equate here, and then this one flag saying that we want the error messages returned to us, and here that we want to get messages of any type, not just error messages, but any kind of messages. And the text unit pointers, it's just a list of addresses, and then the last one has the higher order bit turned on. This first one is pointing to the DD name. This DAL DD name. There's one occurrence of this length text pair, and it's 8 bytes long, and then here is the DD name. So what we're going to do is we're going to copy from the DDN keyword. We're going to copy that value here, and then for the dataset name, we'll copy the dataset name value here. So here it is, the DAL DS name. There's one occurrence of the length text pair. Got the length of 44 here, and then there's the 44 bytes. So it's just very simple. This is how you say dist share. It's dal stats with a value of 8, and this dal indist is the second parameter, and it's also hex08, and it's just a 1-byte field. And then the third parameter, the keep, happens to also be a hex08. And then finally we say, here's the return vol. So whenever you allocate that data set, give me the 6-byte vol seer and place it here. Then for the unallocation, it's just exactly the same format. You've got a one-word pointer with a higher order bit on that points to this control block. It's formatted exactly the same way with the text unit pointers and the RB extension pointer. Just the verb is different. We say, I want to do an unallocation. And its text units are exactly the same. So we've got a pointer to the DD name to unallocate. It's got the token to say what it is. It's one occurrence of this length text pair, and we'll put the DD name here that's going to be unallocated. And then finally, the special token that says force the unallocation. And there's no occurrences, so it's just this one piece. There's no secondary part of this. And this says, I don't care how the data set was allocated, even if it's allocated in JCL with the permanent attribute, deallocate the thing. The main driver of the program here is right here. We read the record in, and we honor these verbs, allocate, unallocate, and list. Anything else, we'll get an error. So if we go to allocate, we'll go to this label called alloc, or if it's unallocate, we'll go to this label called unalloc. So when we get here, we know it's an allocate, so we will first of all initialize the DD name and dataset names that we're going to capture to all blanks. And then we turn these switches off. It tells us that we found a DD name or we found the dataset name keyword on the control statement. And it will start to scan. And what it will do is this part will scan through the white space until it finds the first non-blank. And then when it looks at that non-blank, it will say, well, is it a DSN keyword or is it a DDN keyword? If it's not either of those, then it fails it. So here we say it's a DSN. We'll come down here, and now he's checking, have I encountered a DSN keyword already? And if I have, it's an error. If not, it drops through, and he sets that flag saying, I have found a DSN keyword. And then he points past it. Now, this notation looks a little odd, I bet. Up here we have this literal DSN. And down here, we're just referencing the length attribute of this DSN. So it's going to be 3, or 4 rather. So it's going to say load address 4 off of R1. So point past the DSN equals, and then we've got this subroutine that we're going to call, and we've got R1 pointing at the beginning of that dataset name. R2 has the number of bytes left on the control statement. And he points R4 and 5. 4 is the dataset name target that we're trying to go to, and 5 is the length of that area, and he calls the extract routine. And then he goes to this alloc check to see if there's any more parms. And for the DDN, it's exactly the same. He checks for duplicates. If it's not duplicate, he points past the keyword and then sets up to copy. Again, the target area is going to be DDN, and the length of that area is the length of DDN. And then he goes to extract. And at the very end, once he has processed that extraction from either the dataset name or the DD name, he checks here to see what was the delimiter that stopped us. If it was a blank, then we're done, and we're going to take off and actually do the allocation. If it was nothing, if it wasn't, which the way that extract routine works is it only stops on a blank or a comma, then if it's not a blank, it's a comma. So he points past the comma and goes and processes the next keyword. And here's the extract routine. So the way it works is he says, pick up the character that we're pointing at in R1 and check, is it a blank? If it is, then he returns to the address in R14, the return address, or if it's a comma, he'll return. Otherwise, he stores it into the output area and then increments the input area by 1, points to the next input byte, and points to the next output byte, adjusts the remaining length here. And if it runs out, then we give this error that we ran out of room in the receiving area. And then here he does a jump on count. If there's still space left on the input, he goes back to process the next byte. Otherwise, he drops through and says, I ran out of input area. That's the gist of it. Once we've pulled all our parameters in, he makes one check here. It says, did I get both the DSN and the DD name? And if both of them are not on, then he gives an error. And if they're both on, it drops through. So we say, okay, copy the dataset name to the alloc DDN and the DD name to the alloc DDN and the dataset name to the alloc DSN. These are the two fields that were in the text units for this allocation. And he points to the S99RB pointer and issues the dynamic allocation macro. Yeah, if we have an error, he goes off and produces the error message. If not, then we know he returned the vol_ser to us. So we indicate this data set was allocated, and we also add the volume serial number that was allocated and go print that message. And like I said, because we said I'm interested in messages from all return codes, we have to go and check to see if there's any messages to be printed. So there's this routine right here called print messages that will print the messages if they're there. And then we take the volume that was allocated on, and we do we set up a vol_ser for this get DSCB, and we're going to go and obtain that format 1 DSCB for the data set and print it. If we get an error, we'll put a message out like this: dynamic allocation failed, return code equals reason info SMS code. And this is how we build that message right there. So I'm using a named using statement here. So I'm going to map using the S99RB Desect. I'm going to overlay that mapping on the allocation RB and the allocation RBX. I'm going to put the S99RBX on top of it. And so these are the names for those using statements. So over here, when we see references here, this AL dot S99 error, that means in the S99 error area of this ALC RB, this is the actual RB here, it will pull the error code, the info code, and now this is in the RB extension. It'll get that error reason, and it will print all those things in hex. And of course, once we've printed this general message, we once again will point to this allocation RB and go off to our message routine to print any messages that might have been generated. The print messages routine is pretty simple. When it gets control, it's expecting R1 to be pointing at the S99RB, so it will get that in register 7, and he'll use register 7 as the base register for the S99RB, and he picks up the RB extension pointer out of this RB and uses register 8 for it. And then, so now we've got mappings on register 7 and 8 of those two control blocks, and he'll pick up the number of messages that were generated, and he does a load and test. Are there any messages there? And if they're not, he just returns back to the caller. But if there is, then he will clear this parameter area and set up. He's got the number of messages in R2, and he stores that into the number of messages in this parameter list that's used for IEF DB476. The number of messages, if you take that number and shift it left 8 bits, that's the same thing as multiplying it by 256, and so that gets us the size of the area that we need, and we save that size for later, and we obtain a storage for that size, and put the address of that gotten main area in the parameter list for this IEF DB476. Then we tell him that we want to get the messages, and we indicate that these messages came from SVC 99, not there. We point to the RB and give that pointer to him in his parameter list. And we also save in his parameter list the register 15 return code value. And then once we got that all built, then we point to it and call it. So if we didn't get a problem at this point in the execution, we know we've got a formatted message area that we're going to print. And now we're going to use this second desect, the Desect2 message. This desect maps the area in the buffer that he just formatted, and it's pretty simple. There is a length of this area, so you see there's 2 and 2 and 251. So 251 plus 4 is 255. So we multiplied by 256, but really he's only using 255 bytes per message. This length has the length of how much is used in this whole area. This buffer offset it's always 0. I think they planned to use it for something and never did, so it's just zeros. So the first message occupies this space. The second message is down here in buffer 2. So when we want to get to the next message, if there's multiple messages, then it's the difference between buff 2 and buff 1. This difference is how big this area is, and you just simply walk through the buffer, however many messages that there are. So here's the code that does that. We pick up the pointer to the formatted messages, and we get the total number of messages, and we're going to use this number in a jump on count loop. So this is the loop that's going to just walk through the messages. We pick up the total length that's occupied in that first message space. We back out the length of the header area, so back over here. This length includes the length of these 4 bytes here. So we back that length out, and that tells us how long the message is in that entry. So we check to see is that going to overrun our print line, and if not, we'll continue on. Otherwise, we set it to truncate. We don't want to don't want it to wipe out anything past our print line. Then make the length relative to 0, and we move in. So he executes this move, and he moves it from the buffer to print line +1. And once he's got that, he prints it, and then he advances the pointer. So it's the difference between where buffer 2 is and buffer 1 is. That's the 255 bytes. So he points to the next one, does the branch on count or the jump on count back up here to process the subsequent messages. And after all the messages are printed, then he picks up the pointer to the area where the messages were, gets the length of it, and frees it. So at this point, we have formatted all the messages and printed all the messages.